So something that we've already talked about a little bit is if we're given a function that tells us the location of an object relative to a starting point at time t, or in other words, a distance function, then if we take the derivative of that function, we'll get the velocity function. And then if we take the derivative of the velocity function, we'll get something called the acceleration. So then the second derivative of the distance function, or the starting point function, will give us the acceleration function. So that's kind of going forward, and that's kind of thinking about derivatives. But then we know that we can go backwards by thinking about antiderivatives. So if we take the integral of the acceleration function, then we'll get the velocity function. And if we take the integral of the velocity function, then we'll get the starting point function. So we can either think about this going forwards. So going forwards, we have the starting point function, take the derivative, we get velocity, take the derivative of that, we get the acceleration. Or we can go backwards, we have the acceleration function, take the integral, we get the velocity, take the integral again, and we're back to the starting point function. So if we're given information about the acceleration of an object, we may be able to use integration to determine information about the object's velocity and location. So in this example, we have Juanita who's driving her car. She applies the brakes and the car comes to a stop. It takes 7 seconds for the car to come to a stop. And we're given a function that tells us the acceleration of the vehicle during this time period. So we're given the acceleration function. So in part A, we want to find the velocity function. So remember, the velocity function will just equal the integral of the acceleration function. So in this case, the acceleration function is just negative 2.394 times t. So we take the integral of that function. So to take the integral of that function, we get this, using the power rule, plus c. Now don't forget about the constant of integration. We haven't seen it in a while because we've been doing definite integrals. But this integral is an indefinite integral. There's no limits of integration here. So when you're doing indefinite integrals, you have to include the constant of integration. Now simplifying our answer a little bit, we can get this as our velocity function. Now in this case, we're given an initial condition, so we can use that to figure out what the value of c is. So in this case, the initial condition that we're given is when Juanita first applies the brakes, her velocity is 40 miles per hour, or 58.67 feet per second. So that's times 0. That's right when she applies the brakes, so times 0, that's her velocity. So we can use this to find the value of c. So our initial condition is that v of 0, velocity at time 0, equals 58.67 feet per second. Now I want to use the feet per second instead of miles per hour because here time is measured in seconds. T is measured in seconds. So now to find c, I just plug t equals 0 into my velocity function, and I set it equal to this, and I can solve for c. And so I can easily see that c equals 58.67, and its units are feet per second. So now I can plug that value in for c, and I get that the velocity function is equal to negative 1.197 times t squared plus 58.67, now that I know exactly what t is equal to, using that initial condition. Okay, now in part B, I want to find how far the car traveled while Juanita was braking. The distance the car traveled is given by the definite integral of the velocity function over the interval from 0 to 7, which is the time during which Juanita was braking. So the velocity function gives me the rate of change of the distance. So if I take the integral of that, I'll get the distance function, or the starting point function. And if I evaluate that distance function over the interval from 0 to 7, that will give me how much distance the car accumulated during that time period. So remember, the area underneath the curve, or the definite integral, that's like finding how much of some particular unit was accumulated over a certain interval. So in this case, it's going to be how much distance was accumulated, because I'm finding the area underneath the curve of a velocity function, which is distance per time. So now I just need to evaluate this definite integral. So first of all, I can replace v of t with what I just found it's equal to. Now find the antiderivative of v of t. And now that I have the antiderivative, I can plug in my limits of integration to find the area. And so when I do that, I'll get 273.83 feet. So that's the total distance traveled by the car from the point when Juanita started to brake until it stopped. So we can look at this graph up here to see this represented. This curve that's graphed is the velocity function that we found, v of t. And then the area underneath this curve on the interval from 0 to 7 represents the distance traveled by the car while it was braking. And you can see that in 7 seconds, the car went 273 feet. And in the beginning, the car was going 40 miles per hour.